I did post for you I think it was earlier today, the full set of practice materials for your exam that's coming up a week from Thursday, right? So those are available for you whenever you get a chance to start studying. And I think that just leaves the homework number 9 solutions that I'll, of course, post once the deadline hits. As the last piece of the exam material, the stuff you need to prepare for the exam. We're well past, of course, homework 8 material. We should finish homework 9 material today, and so I'll let you know when we hit the exam 2 and homework 9 cutoff. We shouldn't have any problems hitting it later today. So that's kind of where we are. I just also wanted to give you a brief heads up. There is a small chance that I will need to cancel class on Thursday. If that is the case, I will post an announcement in WebAssign saying that class is canceled. If I don't post an announcement there, then class will be held as usual. So please don't email me to double check if class is still on because you don't see an announcement, because I may not be in a position to respond. So again, if you see the announcement that class is canceled, I'll try to post it by the previous evening, so tomorrow evening at the latest, or possibly very early on Thursday morning. So the announcement will be there, and if the announcement is not there indicating a change of plan, I'll have office hours and lecture as normal. Okay, any questions before we get started? Administrative or logistical things? Okay, so we are working on a static equilibrium problem, and you have a bunch of these types of problems at the beginning of your homework number 9. So let's take a look. What we have is a person just sitting there contemplating a jump. So this is static equilibrium after all. They haven't done anything yet. The mass of the person is 50 kilograms. We're going to take the diving board to be massless just to have one less force to deal with. And the two forces of support will be kind of over here on the left side, toward the left side. So here's kind of a model of this system. I have a mass on one end, and then I have, of course, I can't make this meter stick perfectly massless, but the center of mass is definitely far over to this side. And if I want to use a single support force, I have to put my finger way over here. But I want to make my diving board springy, and so I'm going to apply my two forces way over here. I have one upward force that is way over toward this side. And then in order to keep the end from flipping up, I have to hold the other end down. So this is my force configuration. I have an upward force here and a downward force here. So my question is, if I tell you where those forces are, force A is at the end, force B is 2 meters in, the person's all the way on the other end. What are those two forces? What must they be? So forces alone is not going to help, because the only thing that the forces tell me is that the upward and downward forces have to balance in order for the center of mass to stay put. So if you balance the net force in the vertical direction, you get that the force from support B has to support both of the other forces, which are downward. And if you put in the mass of the person is 50 kilograms, 50 times 9.8, that's 490 newtons. So the only thing that equation tells me is that one support force has to be 490 newtons more than the other one. But there is nothing here that would tell me how much would one have to be versus the other. As long as one is more than 490 than the other, then it'll satisfy the force equation. Of course, we need to also use the torque equation. So as far as torques go, this is the first time where the pivot is not obvious, because this system is not supposed to fail. This system is not supposed to rotate. If something happened and support A at the end here gave out, of course it would pivot around B like this. And if something happened instead where the middle support here, support B, gave out, it would collapse like this. So we don't have a crystal ball. We can't read how might this system fail in the future. It turns out, though, that when the net torque is 0 here, you can really use any pivot. Okay? So the net torque must be 0 around any pivot. The idea here is that the whole object just stays put, so any point is as good as any other to explore as a hypothetical pivot, knowing, of course, that if there were any net torque around that point, we would see rotation around that point, and we won't, because there is none. So this is what the beauty of static equilibrium problems is. It's that you can use any pivot you want, because the net torque should be zero around any pivot that you might possibly choose. Of course, the freedom to pick any pivot is followed by some responsibility. So now you're spoiled for choice. What do you actually use? So I wanted to give you a little bit of a primer in how to pick a pivot so that you can just shorten your calculation. Okay? So here's how to pick a pivot wisely. So these are considerations when you have the freedom to pick any pivot you want, but you want to make your calculations short and easy, not long and hard. So there isn't going to be a silver bullet for this problem that I'm doing that's so simple, but let me show you some considerations that in these hypothetical situations where it will become blindingly obvious which pivot would be good and which pivot would be bad. So here's my first example. Let's say I had a object or system, a rotational system, that had forces like this. Maybe one here, maybe one here, maybe some over here. Let's say I had that. So that's, I think, a total of 7 forces, 5 on one end and then 2 more. So let's examine potential pivots that we might use. I think the first one that most people would feel most comfortable with is to use the exact geometrical center of, if this object is uniform, that would probably be the center of mass. So that's a very natural pivot to use, because oftentimes the center of mass is the center of the rotation if there is some net torque. So it seems like an intuitive pivot. The only problem with that is that if you use pivot A as a choice, as your choice, you have 7 different forces that have leverage against that, so you'd have 7 different torques to compute. So who wants to compute 7 torques? You could do it, but it would just take you a while. So let's say, for instance, examine pivot choice B, where pivot choice B is specifically picked to be at the location of one of the forces. So that's kind of our hypothetical hinge. Now, if that's our hypothetical hinge, one of the forces pulls right at that hinge, and as we know, a force that has no leverage against the hinge cannot exert any torque. You walk up to a door, you push on the hinge, nothing happens. So that means that if you pick pivot B to be the choice, this force automatically exerts no torque. It has no leverage against that pivot. You'd only have to compute 6 more. So you'd have to compute 6 non-zero torques, because only 6 forces have leverage against that pivot. So what about if I chose C? How many torques would I have to compute?
6.
Again, I'd have 6, with one of them being 0, and you can hopefully see where I'm going with this. Where do I pick the pivot if I want to compute as few torques as possible? All the way over here. If you pick that, you have 5 forces that you can just ignore in your torque calculation, because all 5 of those forces are pulling at your hypothetical hinge. They have no leverage, and so then you only have 2 forces with leverage against that pivot, so you only have 2 torques to compute. So would you rather compute 7 torques or 2 torques? I would rather compute 2 torques and be on with my day, right? So that's one consideration, is to pick your pivot such as to minimize the number of torques. So minimize the total number of torques you have to contend with. So if I take this reasoning and I apply it to my problem, I really would only want to consider 3 possible choices. 1, 2, or 3. Because each one of those choices knocks out a torque and I only have 2 to compute instead of generally I would have to do 3, right? So I would not, for instance, want to pick the center of this diving board, so that would be 2.5 meters from either end, because none of the forces act there, and so therefore I would have 3 torques to compute, which is 1 more than I really need to do. Okay? So that's the first consideration about picking torques and picking a pivot, such that you're trying to minimize how many torques to contend with. Remember, you can really pick anything you want. The other choices aren't wrong, they just end up taking longer to finish your answer. So time is of the essence, especially on exams. So here's another consideration. So let me put down again some kind of rotational object. Let me put down some forces here. Just make some up, let's say like this. So that's actually very similar to what I have. That's the force configuration basically in my problem. So I already learned from the first bullet point that I would not want to consider any choices besides these 3. Let me label them, I guess, A, B, and C. And let's evaluate each of them, A, B, and C, as potential pivots. So each of those, of course, is going to be 2 total torques, but I want to now make a distinction with the 3 forces that I do have. They're going to fall into the 3 categories of variables that we have. So we, of course, have the know it, which I mark with a question mark. I have the want to know it. No, sorry. I want to know it is a question mark. Have it is a check mark. And then don't know, don't care, which comes up, of course, because you need to adequately describe the system, even though it's not mentioned in the problem. So that's, again, something you have to really get around in your physics problems. You can't be too obsessed with the list of things that are given and asked for in the question. There may be other things. You should just look at the situation, try to start writing down what's true about the system, and go from there. Okay? So let me put these forces into categories. Let me put it as want to know it, have it, don't know, don't care. So let's say I have one of each, just as an example. So we know each of them are going to have 2 torques, but the question is torques involving which 2 forces. So if I pick pivot A as my choice, the thing that I want to know is not going to appear at all, because that has no leverage. So the 2 forces I'd get are the have it and don't care. Have it, don't care. So we don't want that one, because the very thing we want is not even going to be in the equation. So that's not going to be helpful. We can evaluate pivot choice B. Then the thing we know is not going to be mentioned in the torque equation, because it has no leverage. And the forces that have non-zero leverage are going to be what we want and what we don't care. And then finally, for pivot choice C, the very force that we don't know and don't care about, great, it won't be in there. We'll have the thing that we want and the thing that we know. So which one is it that, out of these 3 pivot choices, which one would we use? C. We'd use C, this one. It's a great way to get around forces that are involved that you don't know and don't care about at all. What you do is you stick the pivot there, so then you never have to care about what they are. Okay? So hopefully with these 2 different, this advice and this advice, this one you want to kind of, I'll say, bury unwanted forces. So factor number 1 there is minimizing the total number of torques you have to contend with. And then secondly, to bury or get around forces that you don't know and don't care about by picking the pivot choice to be where they act. So between these 2 considerations, you can choose wisely to have as few torques as possible. So in my first example, obviously, I tried to draw a big wedge between them. It was the difference between 7-2 torques and 2 torques. That's obviously a huge difference. In my problem, it's really just the difference between 3 torques versus 2 torques, right? So I can't get away with computing less than 2 torques in my problem at hand. And then over here, varying unwanted forces. Now, obviously, that's not even applicable to my situation, okay? But let's say that I asked you just for NB, right? So I just asked you for NB. You could have gotten that not knowing nor caring about NA by picking the pivot here, okay? You can jump straight to solving for NB with the torque equation because you can make it so that NA is not even mentioned. Now, that's obviously not what I did. I want both of these. The one thing that I might not want to do is pick my pivot here. And the reason why is because if I pick my pivot here, the only force out of these 3 that I know is going to be not mentioned. And I have 2 forces that I don't know that will be in the torque equation. That's okay. My torque equation would come out with 2 forces that I don't know. I could use the force equation, which has 2 forces that I don't know, and I could algebraically ram them together, right? You can always do 2 equations to unknowns. But what I will suggest is, why do that? I'm going to just pick one of these as the pivot. Let's pick this one. And so make sure you can see that if I pick the pivot there, NB is going to just pop right out. We're going to have a number for NB coming out of the torque equation, okay? And once we have that, well, NA, we don't have to go back and do another torque equation. We just take our value for NB and we'll get NA right there. So I'm going to go ahead and do it like that. And then once I've finished it doing that way and discussing the answer a little bit, I'll go back and show you that, of course, the other pivots are just fine. It would have worked just fine. You can practice any one of these problems. Do it with one pivot, get the answer. Try it with another pivot, make sure you get the same answer. Okay, so let's go ahead and proceed. Torque of A plus torque of B plus torque of G have to all cancel. And my pivot choice makes it so that this torque is 0 right away, okay? So that's a really important point, is that until you pick a pivot, you can't say which torques are 0 or plus or minus. But everything flows from the pivot, okay? So once you pick the pivot, so from the pivot flows which torques are plus, 0, or minus, what their R values are that are used to compute the size of the torques. Everything flows from the pivot. A lot of times what I see students do is have the ever-moving pivots. The pivot just kind of moves around constantly. They pick a pivot, compute a torque, then they move the pivot and compute another torque, and then they move the pivot. You got to pick it one and stick with it. Okay, it's like you can't have a drifting origin in a problem. You can't have can't have a drifting pivot. So once you commit to a pivot, all your torques have to be computed relative to it. So let's go ahead and do kind of like my rotational free body diagram. There's my pivot. I'm going to omit the NA entirely because that's acting at the hinge, so not relevant for my torques. I'm looking at a competition between NB and FG. So NB tries to drive the system around like this. If it were in NB, it would drive the system counterclockwise, which we call plus or minus. Plus. So the torque of B relative to this pivot is going to be plus. And how much leverage does it have against that pivot? 2 meters. So, of course, it's not just up to NB, because that would drive a counterclockwise torque and angular acceleration. It's being canceled off by FG, which causes a torque in the opposite direction. So notice I'm always tracing my circles around the pivot. I may not always bother to draw the complete circle, but you should always imagine that your pivot that you've chosen is at the center, I see students sometimes doing this. Where are you going? Okay? The pivot has to be in the middle. Okay? So not like this. So the torque of gravity is going to be clockwise or negative. And of course, you should wind up with a mix of positive and negative torques because the net torque has to be 0. If you somehow find that all your torques are plus or they're all minus, something went wrong. You have to have that the net torque is 0, so you have to have, for starters, that some torques oppose other torques. How much leverage does that force have relative to the pivot? 5 meters. That's 5 meters. Because that acts 5 meters from the pivot. And so the force of gravity has more, I guess let me phrase it in terms of the torque, the other force. So this one has less leverage, right? That only has 2 meters of leverage, where the other one, force of gravity, has 5. So if these torques are going to balance, if one of the forces has less leverage, what does that mean about the force? Has to have more force, okay? So our prediction, just from intuition, is that the force that's closer into the pivot has to exceed the force that is further from the pivot. Let me point that that is not at all in any way contradictory from our previous findings, right? We predicted that NB was going to be bigger than NA, or bigger than force of gravity alone, because there's this extra force in there, right? So now we're imagining it as a competition of 2 forces. It's much in the same way as when you're seesawing with a little kid, right? If you're seesawing with a little kid, you weigh more than they do, right? You have more force, so you have to sit closer to the pivot. You have to have less leverage, right? The only difference now is that in a seesaw, of course, both of the force on you and on the little kid is driven by gravity. So they're both downward forces. So you have to sit on opposite sides. Now, both forces are on the same side of the pivot, but one is up and one is down. So even one force is up, one force is down, but they're on the same side of the pivot. So one wants to rotate it counterclockwise and one wants to rotate clockwise, and if conditions are just right, they'll cancel each other out. Okay? If you need further evidence, here's what we have. We're pretending that our hinge is here, and we're imagining competition between this force, which wants to rotate it this way, and the force of gravity, which wants to rotate it this way. So obviously, I have to push very, very hard to hold this thing up from here. Okay? You believe me? Okay? It's starting to hurt my finger. So yes? Okay. It's a lot easier to hold it up from over here. Okay? Okay, so let's knock it out here. Our torque formula, we've just decided that this torque is going to be plus, this torque is going to be minus, and then we just need to fill in the sizes. Remember that the size of the torque is RF sine theta. Hopefully you can see in this that both of these forces are entirely tangential, so sine of 90 is 1. So all I have to really do at this point is throw in RF. So this will be RBFB, and this will be RGFG. We can, of course, this is a normal force, so we should probably label it as such instead of just calling it F, and then F, the other force is gravitational, so we can label it like that. So if you solve this, we basically just once again get that the product of the leverage times force has to be equal to the other guy so that that way they balance. And we have all these numbers. We have that the force of gravity is 490. We said that that had a leverage of 5 meters. The other force only has a leverage of 2 meters. And so we can find out how much force that is. And if you calculate that, we can find that it's just the ratio of the leverages times the other force, and that number comes out to be 1225 newtons. So a 1225 Newton force with a leverage of 2 meters can successfully cancel out the torque of the gravitational force, which is 490 newtons, but acting with a larger leverage of 5 meters. So, like I said, NB will just pop right out, and we'll just have it right then and there. We're done finding NB. We picked the pivot wisely so that NB popped out on its own, and now, of course, we can plug in. If NB is 1225 newtons, and mg is only 490 newtons,